Okay, thank you. Okay, thank you for still being here. So I think I want to thank the organizer. I think it was a great conference. And okay, and yes, you remember that we had such conference in 20 years ago, and I think it was very important. I think to just for a full generation of researchers at the time. So okay, so I'm here to clean the room. So because I'm the last talk, so okay, so be cool with me. So don't put too much waste. Okay, so I want to speak about say about shape spaces and so on, and more or less, I think the idea is that I want to say that I think we have a quite mature technology to do quite a lot of things with shapes. And basically, we have things that if we work with this Riemannian framework, and if we have good metrics, we have a lot of way to do statistics and also to do longitudinal analysis, as we have seen in the talk of Stephanie. But I think that the thing is that, there is still an important question about the choice of the metric, how we build that metric, because that metric is something which supposed to be here, and we can solve problem, and after we can apply, after all the parametric matter to extract some important information from it. But okay, I think this metric is something which is important, and how to deal with this kind of thing. So this is basically what I want to say, and just to make things, because we want to extract some meaningful parameters. So this is basically, okay, this is I will talk about work with many people, but this, I think this, the end of the talk is mainly a joint work with Barbara Gris and Benjamin Charlie. So, first I would like to recall a few things about shape spaces. It starts with Darcy Thompson, as most of you knows. And Darcy Thompson, the interesting thing with Darcy Thompson, I think it's developed the theory of transformation because he wanted to make connection between shapes. But he was thinking that this transformation is just a way to reduce the complexity, because he was really aware about the complexity of things that happened at a very micro level between things. So we have very complex phenomena, and if we try to describe them, we enter into a lot of complication. And when we go from the micro scale to the macro scale, from micro scale to macro scale, we need to have reduction. We need to deal with all this thing and to simplify things. And so for Darcy Thompson, this transformation is just a way to say, okay, we have a body. We should be able to move. We should be able to act. And so there is some kind of constraint and reduction, so that in fact it should be simpler at some level. Simple at some level. This is the idea. So now computational anatomy is just okay to study the different shapes. We could say it's about matching shape, but it's about also moving inside shapes using basically geodesics. So the metric is very important, because if we change the metric, we'll move in a different way. So we cannot say that the metric is just something which is like this. It has a lot of consequences in the way we are doing statistics, for instance, shapes. But okay, so we have a quite general. Okay, can you see the pointer? Yeah, okay, so that's why I moved to green, because I could not see the pointer on white thing. Okay, so we can work this idea is to be able to work on different things, so on images, on shapes, and so on. Even these fibers and so on. Okay, so the shape space, I think I would say morphometry, because there is a lot of way to do shape spaces. Anush shows a way to do it, and there is many ways. So I will talk mostly about a way where you think that you act an object with a group of transformations. So the basic 101 thing is that, okay, the idea is that we have a group of transformation diffeomorphism, and we act on objects. And so what the basic object is to look the homogeneous space, I mean the orbit, which is generated by a group of transformations. So we have a connection between object and transformation, and the idea is that it's simpler to work with transformation than to work with the object. Object can be very complicated, but usually this transformation, as Darcy Thompson was thinking, should be simple. Okay, and so the story is that if we have this, you look at the orbit of a group of transformation on some kind of template, we can equip this space by a distance if your distance on the group is right invariant. So it means you have some kind of property, and then more or less you can induce a distance on the object space by just trying the simplest transformation, you know, that transform your shape A in shape B, more or less, that's it. So there is something which is very simple into this, and the story is that in fact we just need to build a metric on the group of transformation, and since on the group you want to be right invariant, you just need to choose a metric as the identity. So you could say we have just one high dimensional parameter, which is the choice of the metric for small deformation, and you have all the machinery which explain you how to go from small to large deformation. And you can do it on many things. That's the idea. Okay, and so we have this framework, and usually when you have to solve a problem, you have to deal with data attachment terms, which are very important. And now we know how to do it. Okay, 20 years ago, we have no idea about how to do it, but now we know how to do it, and okay, Irene explained it in his talk. So we have currents, we have oriented manifold, we have normal cycle, we can even use optimal transportation if you want, so we can do more or less what we want. And so we can build geodesic between shapes, and we can have yeah, I should not. And okay, we can do this stupid things as just shooting from a sphere to something, and okay, how to do this kind of thing. I think that's stupid because it's, okay, biologically it makes no sense about doing that. But we can, okay, this we can do it. Okay. So, Control Q, no. Oh, the bunny does not want to go away. You want to stay here. Oh, not good. Oh, okay. Okay, stay here. So, and we have, I think we have now a very solid numerical framework. So we know, and we have this Cheops, which is really, really nice. Just been developed by Jean Fédy, Benjamin Charlier, and Joanne Grenès, and Jean tried to advertise this kind of thing. And so we have now a lot of good framework, so we are happy. I think that there is still an open question, and I want to say that, okay, I like this slide with Greenender, and Greenender was asking, okay, about pattern recognition, can we, okay, understand what's going on this? It's not just about just doing mapping, but can we understand what's happening in the data? So understanding means we want to test a hypothesis, we have some idea of structures, and we want to say something interesting about. So I think this is still an open question, and all of us, we are trying to go from non-parametric to parametric modeling in different situations. The last talk was exactly about that, I think, okay, so I think this is really the important thing, how to put structure in the model in a nice way. So what we have, we could say, what the freedom we have to put some prior to learn something, we could say, okay, if we stay in the framework I was presenting, we could say we could play with a metric. And François Xavier was exactly explaining this, how we can try to learn something, to play with this metric, which is the initial thing. That's the way. We could try to say, we want to have more, I say, semantic reduction to mean to have some more meaningful latent variable. We like to have this kind of thing. So that's a different route. And so, okay, I think it was, I like to mention this paper by Anuj, because Anuj is complaining that I'm not citing him enough. And okay, this is a very important paper, which is about this, how to understand biological growth and how to describe things. And we know that's very hard to make things which works and, okay. And okay, there is a paper by RCD, Penek, and Ayash about trying to say that we have some transformation which is locally affine or locally rigid. And you have the idea, the paper by Alain, which is about constrained evolution, saying that that's something which is quite different. It's about to say that we cannot go everywhere. So we could think about transformation where we have some constraint and dimensionality of where you can go. So it's some kind of going back to fully non-parametric framework to something which is more parametric framework. And so the kind of thing I will try to develop here is the idea about to describe, to have some kind of vocabulary for the deformation, or to be able to have something more discrete with less parameter in a sense. Okay, so the better is to go. So for the first attempt is this one, and so mainly it was the work of Barbara during her PhD. So this is to say, okay, we could have what could be a deformation models. We know in biological shapes also there is some kind of modules. We know that some part of the shape is behaving like that and other part of the shape is behaving like that. We have this, and we have some kind of a lot of regulation between all these parts that we cannot really modelize, but that exists because we have regulation because, okay, it should work at the end. So it cannot be completely independent. So this is very simple. We could say we could have locally a local translation somewhere. It's supposed to work, but okay. So here you have what you have. You have just a translation in what direction. So you could say I have a parameter which is locally the strength of the translation, so that's pretty simple. We could say that now we have not a fixed translation, but we can have any translation like that. So you can see that you can have a parameter, a control parameter, which is the strength of this translation of the intensity. We could have something like local scaling, like this, rotation, or we can have dots and we have different translations. So we can build something like that. So here we can independently choose we have 3 control parameters, but also we could say direction is a control parameter. So, okay. Let's see that. So, okay, we can imagine a lot of different things, and we will do something different at the end. But, okay, if we try to think about something which has some kind of general framework, we would say that, in fact, we have, for a deformable module, we have something, the first thing is a geometrical descriptor. I think this is a description, this is the thing you need to describe the module. It could be a point with a vector. This is this kind of geometrical object which is describing the modules. So we could say it's a manifold. And we have now, given that structure, I could say that structure is something, when you want to model, you have this idea about what you should have. But what you don't know is that the control, this could be an interesting latent variable, this control space, which is a finite dimension. And so you will say that now, given O is a geometrical descriptor, and given some control, which is finite dimension, here you generate a vector field, deformation. So here, for instance, you have the geometrical descriptor is just given by these 3 things. It's fixed, it's one-dimensional, and you have a control which is like this. So it's a very simple local translation. Okay, so if you have local scaling, you could say that you need to say where you have your local scaling. So you need to have your manifold is just a point, so it's just RD. And you have just one control. You could say it's a local fixed translation. So what you have is you have to give a point and a direction. So your manifold is as RD cross SD minus 1 because you have the location and the direction, and you have just one dimensional. But you can imagine all the things. Okay, so now what we have is we call it a feedback action because at the end we have several modules like that. And so all the modules are able to create a vector field, a transformation. But now we have to understand how you act on yourself. You know, you have this vector field which will be acting on the geometrical descriptor. So you need to have this feedback action which says that given geometrical descriptor and given a vector field, how I move, how I evolve my geometrical descriptor. So there is a nice framework which has been developed about sub-riemannian geometry by Sylvain Arguier in his PhD, which explains how to say that I have an action which is smooth and so on. Okay, I will not enter into this detail because it's quite technical, but whatever. So, and now if we want to try to close something, we need to have a cost. The cost for generating a vector field. So zeta, so I will have zeta that explains the zeta mapping is explaining how I can, given a control, generate a vector fields. And the zeta mapping will be, given the vector field, how I have a feedback, how I can move, deform my control parameters. And so, for instance, if you, and so, okay, yes, I was talking about the cost. And the cost explain, you know, how you pay to do that. So you have to put price on that because you have, the thing is that usually when you have data, we have some missing time. We can see data at some point. So we have to fill the gap between the two. So ways to build Geodesic, and Geodesic is something like minimizing a cost. So we need to have a cost somewhere. Okay. And so we want to have quadratic cost so that we are building some Riemannian metric here. And so, for instance, just to have an idea, so we have a very simple geometrical descriptor here. And if you look at when when you have this vector field, so the vector field moves the points and moves the geometrical descriptor. So the module is evolving as the shape will evolve. It's not static, it will evolve with that. That's something which is important. And here, you know, when you have this, just a direction, if you move, okay, the direction will move also. So you have this feedback on you. Okay. So, in fact, we have this kind of thing where we have here, we could say a typical module will be something like that. So you have the product between the M, which is the space of geometrical descriptor. We have H, which is the control. And now with this, we have the zeta application, which gives you what kind of field you can generate given the position, given the choice of your geometrical descriptor. You have zeta, which is the infinitesimal action. What is the feedback you have? And you have this cost. Okay. So we have seen an example of this kind of framework. So I think the core problem, one of the core problems is the design of the cost, because you could generate something just, if you choose the cost arbitrarily, there is no way to make things really meaningful. Maybe this will explode when you will try to move. So in fact, you need to have a condition on the kind of cost you have. And a way is a condition, okay, it's a technical, no, I think it's quite simple condition. It's, we call it UEC, Uniform Embedding Condition. We say that, in fact, you should have an embedding vector space, Hilbert space of vector fields, so that, you know, when you generate something, the cost you pay should be able to control the norm of this vector field. So you have to just think about this. The cost you have should be related to the cost, to some cost, Hilbert cost for the full vector field. That's the idea. Okay. So we need also to, I mentioned this geometrical description for the modules, but you have the shape itself. It could be points or images, but okay, mainly points in the example we will see. And so we call it silent modules. It's just, you know, it could be just a shape, but with no controls. It's just a passive shape. You have something which is passive. The deformable modules are active. So you generate no field and you have no cost. But the thing is that, okay, we like to say we have different modules. How I could be able to do some kind of composition of this. This is a very old idea about pattern theory, to have something which is compositional. Okay, so we have some kind of compositionality here. Means quite simple in the sense that if you have different modules, you can build a higher dimensional modules where you by just a combination, and what you do, it's quite simple. In fact, you say that the new space of geometrical descriptor will be the product of the individual geometrical descriptor. The action will be just the straightforward way to generate the action. For the control, you have the product space. So we have the number of control will be added. The dimension of the control will be added. And now the vector field will be what? The global vector field will be the addition. So we are addition the vector field of all the individual deformation modules. And the cost, we have the additive cost. We could think about all the composition rules, but okay, we have this simple one. And the thing is that we can prove that under this composition, if you have individual modules, we are satisfying this uniform embedding condition. So when you compose them, it's also satisfying this uniform embedding condition. Why is that important? Because more or less this uniform embedding condition says that you will be able to compute geodesic. You will be able to minimize things, and you will have solution. So that's important. So in fact, we could say that given this, we are defining what is called a sub-riemannian structure, where we go, okay, when we have, at the highest level, we have a deformation modules, because a combination of deformation modules is the deformation modules. So we have one deformation modules, and we have this mapping. This is the way you generate vector fields. This is the infinitesimal action. So what you have, you know that when you are somewhere on your manifold, you have some subspace of all the possible movement you have, and which is describing by the composition of these two things. Okay. And so if we have smoothness enough, we have condition to be C2, we can, in fact, we have existence of minimizing geodesics, and we can do shooting algorithm. It means if you have some initial condition, you can shoot for any time. Okay, so I will skip maybe this because I want to. We can do the usual thing. You like to have it to build atlases. You mean you have different shape, and you want to build some kind of mean shape. So we can do this kind of thing. We have to introduce the Hamiltonian, so which is associated with the optimal control problem, and we do it by just minimization, and we have to update the template. So we have hyper template. I will show you an example in this. Okay, but we can say, I think we can, in that framework, we can try to do the same, extend the same kind of geometrical thing we can do with the usual Riemannian framework. So we have this very simple thing. So you have these curls of different, it's inside the human phylogeny. And okay, given this, you would like to say something about, what's happening. You see that the skull is growing, the jaw is also has different displacement about that. So I think it's some toy example, but it's just to have an idea. And so we can have all the different skulls, and you have the hyper template, and okay, you can learn something, and here this is what you learn. So you learn some kind of template which is reasonably in the middle. But the thing is that we have all these things, so maybe this is not so easily interpretable, but in fact all these things are coding different deformation modules. You can have in this, you can have translation. You can, with a triangle, you could say this is a local scaling at a given scale. When you have a circle, it's a local rotation at a given scale, and so on. So you could say that you could try to optimize the position of these deformation modules, and more or less we can do it. So just to show some few examples. So here I will see a shooting. So it means we'll do the matching between this is the template and this is in black. This is the target. In purple, this is a template. This is the initial momenta we need to do the shooting. But now, what is interesting is that what will happen, what you see in red, for instance, here maybe okay, that's easy to understand. So we have local scaling here at a given scale. And so when you see this red, it means that locally you see that you are growing in this region. Okay, that's not a big thing. That's quite clear that the scale is growing, but we see it here. Now we have some kind of fixed translation, so it means we are moving back. You know, this part is moving back. You have rotation. So we have this kind of thing. So we could say, okay, that's a way to try to go to a fully non-parametric way into something where we try to discretize, to put some prior, and to try to understand what's going on. So what you see here is just the evolution, you know. And you see massively, you see this control parameter is interesting. Okay. Okay, so this is another example here. Okay, and here you have. Okay, so I think it was a current situation, and so we have explicit. The thing is that for the generative modules, we have something which is explicit. We say we have some local scaling here. That we can describe, given the control parameter, it's clear that we create a shape, an evolution. We have this local translation. We have this, so everything is explicit. But it depends that, in fact, if we look to this, where we have growth of leaves here. So we have this is taken from a paper by Dasgupta and Nath in the plant cell. So we have 3 leaves here. And if you look at that, what you see is that, okay, if they put some small dots of ink and look at how it grows. It's so simple thing. And so when you look at this, you see, in fact, here, this is base-parallel. It means it's if you look at, okay, the size is, the height is 38 millimeters. This is 100 millimeters. And if you like, okay, you put some regularly spaced dots. And now, if you look here, you see that, okay, the dots are much closer here and larger here. So what does it mean? It means it's growing from the base here. So it's small, it's growing like that. So we have, because that's the way this plant is growing. It's growing from the base and not from the top. And we have a gradient here. It's moving like that. But we could have the other situation. So where it's acropetal, what it's not growing from here, but it's growing from the top. And so you see these two things go from 90 to 495. So large deformation. And okay, we see this thing. Here it's diffuse. So if we think about shape, and if you say, okay, we have this dark point, this black point here, but if we do not have them, and if we just look at the boundary, okay, so in fact we will be able to go from one shape to the other, but maybe it will make no sense because we could see that biology is quite complex. It could have a lot of different behavior, so we have not the same one. There is no reason why you should have one metric which is the right one. So if we have all the information, that's okay, but usually we have not the information. We have partial information. Someone can say, okay, we have this, but people usually, they have some good idea to think that we could have this kind of structure or this kind of structure and maybe not this one, or they want to test. So this is exactly the spirit I would like to develop here. So I think that we have this kind of thing which is the basic thing we have seen is some kind of stretching. We have stretching, horizontal stretching, and horizontal, vertical, and this kind of thing. So it means what people will tell you, I think, if you talk with someone working on this, he will say, okay, it's expanding like this, and okay, but it's more or less uniform, this kind of thing. He will not say, I have a local translation, because local translation is ambiguous. We do not know if this is a global translation of the shape, or if this is just something which is local. Rotation also is ambiguous, because you can just rotate the full shape, or it is just local. So it will say something which is just about the deformation of the metric. Okay, so I think we could say, we could think about, we want to put information where we say we have order 0, which is a local translation, but we have order 1, which is some kind of local stretching. We would like to put this kind of thing. And that's clear that people know from elasticity that there is something which is the infinitesimal change tensor, which explain you what the change in the metric locally when you move. So you could say, at that point, you could say, oh, okay, I will do some kind of elasticity model and so on. But this is not the thing we want to do, because we think that, in fact, it's when we enter into this, that's a very interesting route. But there is a lot of things, because you have to describe a lot of things. And usually there is many things we don't know. And in biological shape, there is some genetic regulation, there is a lot of things. It's not just about mechanics, it's a lot of things. So what we think is that what we should keep, that's clear that this is a very meaningful thing to talk about strain tensor, because it's something that makes sense, which is intrinsic to the shape. So the strain tensor is what? Is when you have when this is infinitesimal strain tensor, when you infinitesimally move your shape by a vector field, it's given by the differential of V plus differential of V. This is a symmetric part of the differential at a given point. And so this is a symmetric tensor. You can just, okay, in 2D, and you can have the same in 3D. So you could say it's, you can diagonalize it, and by rotation by two coefficients. And the two coefficients give you have some principal direction, give you, okay, the relative rate of increase in both directions. Okay. So the thing is that what we could say, what would make more sense if we think at the leaves, we could say, in fact, what we have, we could say we have some kind of model where we have locally some kind of orientation. This is the R matrix, which is the rotation. We have the different rotation in different places. Okay, like this. And we could say that the strain tensor should have this kind of shape. It means you have this coefficient, alpha 1 and alpha 2, which is the increased rate of expansion or contraction locally, and this matrix. So I think this is the kind of parameter you would like to work with. So we'd like to describe this. Maybe we'd like to say something about rotation. And we could think about, if you look at the leaf, we think that it's mainly low dimensional. We know that if it grows like this, it will grow like that at this thing. Or maybe we'd like to understand a little bit more about that. But we know that there is some, because the plant should grow in some sense, that cannot be arbitrary between the beginning and the end. So when we have different parts, they have a lot of connection between them. So we could say that, in fact, what we needed to have this CX is just a different relation between that. And I think we could say that, in fact, we have just one matrix, and now we have a very low dimensional control, which explain you could have, I will give you some example, for instance, it's mainly expanding vertically or expanding vertically, but it's the same expansion vertically, or it's growing linearly, or it's maybe just quadratic something, but okay. I think it's low dimensional. Okay, and so the thing is that we will need to build something which is implicit module, in the sense that you will say, okay, you have this, and you will say, I have this rotation, and what I want to do, I want to put the constraint. I want to put some constraint on this strain tensor, but I will minimize. Okay, the thing is that I will say, I have this constraint, so that okay, SI. Okay, there is something which is missing. What is SI? SI is SI is a symmetric part of the differential of the. This is the infinitesimal strain tensor of the actual field you are trying to build. So what you will say that you want to put constraint on this strain tensor, infinitesimal strain tensor, and okay, you have to minimize to some energy, to some metric. Maybe you can use the usual Gaussian or whatever. There is some discussion about that, but okay. You have this, but you say that. You just describe things locally. you want to talk about this train tensor. After, okay, you have to file something which is consistent, globally consistent with all these constraints, but this is, you cannot ask this kind of thing as someone which want to model things. So this should be implicit. So you have some inversion. You have to invert the system here. But you see that the real number of parameters is given by h. So h is a small dimensional parameter. And so now, when you solve this implicitly, given h, you will have a vector field V, and you will be able to define the cost, which is given by also the Hilbert, the square Hilbert norm of this velocity field. Okay, and so let's see. So for instance, here you have, it's a very simple thing where you have just dots. You have a module of order 1, so you have you have 5 times 3. And so mainly I want to express that, you know, there globally, I want the strain tensor to be just horizontal, so it can grow in vertical way and not in the horizontal. No, here this is the horizontal direction and not the vertical direction. So it's just the infinitesimal. So this is just a vector field, but okay, I move it by just, you know, a certain factor. So this is x plus something times this vector field. There is no integration here. Okay. But what you see, you have this very simple thing is that, you know, this is a control and you create this but what you see is that vertically is just constant. So you can have the, this is the opposite. So you mean it can shrink vertically, but horizontally it keeps everything constant. You can do something which is anisotropic here. So here what you have, you see that, you know, on the left, there is more contraction than on the right, for instance. And so you can easily imagine the kind of structure you can build. And okay, and so now if you have also the same thing, so you have this, you say you have just a factor in you have, okay, here the only thing to have this kind of shear behavior is just the rotation matrix are not vertical, but they are just tilted by pi over 4 angle, by pi over 4 angle. Okay. Oh, yes, maybe this one is, yeah, I like this one here. Okay, that's very simple, but what you say that, you say when you more or less, if you the dilatation rate as you change the sign between the two sides. So when it shrink in one side, it has to expand in the other, and so you create this kind of behavior, bending behavior. Okay, so now we can try to mix. Say we can combine. So one module will be just a set of blue points, which give you some constraint on order 1. You can build another module which is just order 0, which is local translation, but it looks like a non-parametric part. It means the main, you could say the main thing is just driven by the order 1, but you need to add another layer. Because when you have data, they are very different. They are not just parametric. So you need to add some non-parametric layer, which is given by the red point. And okay, you can have this contraction, you can add things. And so here, you know, for the cost, you can have parameter between, you know. Okay, I did something wrong. Ah, woo. C'est tout bête. So you can take your place.
I think there are some real issues in your theorem.
So, okay, that's now the thing is that I was running out of batteries, that's why. So now that's okay. Look, I have 2 minutes. Woo. Okay, so what we have, I think we can. So we have cost. I think we have. We could think that we have the shape now. You describe the different things that can happen, and you could have put weight. So if you, I think you have lambda 0 and lambda 1. If you could say you have this rate, and if you lambda 0 is very high, it means you can just use the parametric setting more or less. And now you can mix them, or you can put lambda 1, which is very high, so you will just use this kind of just local translation, which is in fact this, the non-parametric, the usual LDDMM framework in a sense. Okay. So we have to add also the silent module, which will describe the shape. And now we have to think about what is the feedback action. So because now the geometrical descriptor for the modules of order 0 will be a point and a matrix. It means the local orientation. So you have to explain how you move such things. So the point will be transported by the velocity, and now okay, this is not, yeah, okay, this is R. So, no, that's okay. So this is for, this is for order 0. You have just a point, so it's transported by the velocity. When you have order 1, which is the geometrical descriptor, is given by a point and a rotation matrix. So you will move the point by the velocity, and you will transport the rotation by the skew-symmetric part of the differential of the velocity of the vector field. So you will use this skew-symmetric part to update the rotation. And so we have all the theory to describe that. So we can build the Hamilton system, and we can do the shooting for this kind of thing. Okay, so this is a very simple thing. So this is geodesic example. So it's like very simple geodesic. So you integrate, you have the initial, and now you integrate, non-linearly integrate. And so, okay, here. So what you have here, you see something wrong happened, because it's you have all the red points are moving away like this. So it seems like you have a front. But if you look what that is, this is a situation where, you know, if you look, okay, this lambda is lambda 1. So I'm just using the order 0. So it's typically the typical LDDMM behavior. So when you, I have an initial condition where I more or less I say I will move, I want to move up and down the top boundary and the bottom boundary. And so what you see is that everything is more or less localized along the boundary. And so in fact, that's for large deformation. I think this is something we know and we don't like so much about this kind of thing. And we'll see for the leaves that has consequences. But now if I reduce, now I'm allowed to, lambda is equal to 1, so I'm allowed to use the order 1 more easily. So what you get is this. You know, it's much more reasonable. And you can, okay, decrease. So it's easier and easier. Oh, no. Okay, it's this one. Yeah. Okay, so now it's regular. You can do it in an isotropic way. So here it's just order 0 more or less, but okay. Yes, let's see this one. Yeah, okay. So now I put this left-right dissymmetry, and so what you see is that you create something which is bending now. So you can build a lot of interesting things. Okay, so maybe I will go to this because I will show you some. I think it's still a very preliminary example, but okay. If we go back to this thing, so we have this this leaf example. So now what we have is the basipetal thing. So it's growing from the base. And yes, it's growing from the base. So it means on the top, it's not, you know, it's more or less rigid. And so here we can say we have something like a shape like this, but we have to choose the control parameter. So if we just do the usual LDDM, usual, you know, metric, the kind of metric we are usually using. So here we have some quite large deformation because you see it's, this is the initial shape, this is the end shape. And what you see is that in this mapping, I'm just using the boundary information using varifold. So I'm not using any information, interior information, because I say that, okay, 3 minutes, that will be okay. I think you're lucky because I will be on time. Okay, so, but this is an important thing because what we see is that in fact, what we have, I think we are just using the boundary information. We have nothing about the parametrization. It's parametrization invariant. So, but we see what the metric is doing, you know, when the information is missing what the metric is doing. And so what we see that we have compression on the boundary and we have dilation in the interior. And so the mapping is completely wrong. It's not like this at all here. Now, if we put this first order thing, what we have, we can create quite easily this kind. So we can have this mapping. You see it's not perfect. But you have what you see is that you have a grid behind and you have that this thing is just explaining that, you know, it's, you see at the end the deformation of the grid. So you have no deformation on the top and you have deformation here. Okay. And so if we add a little bit of non-parametric, so we have a better matching. So we do not try to have a perfect matching in this. But okay, we can, if we think that we have not exactly this parametric thing, but something which is deformed, we can deal with that. And so this is just a model here, very simple one. So the other way, this is the acropetal. So you have a much larger range of deformation, and we have the same thing. In fact, it's, you know, it's here maybe you do not see, but you have a lot of compression here, you have a lot of compression here, and you have a lot of dilation here. Now, if we do it in this, we add the order 1, we have something which is completely regular. Here, not regular, but you see it's going from, you know, the rate of dilation is increasing from the bottom to the top. And now we can mix things, so here we can have a perfect matching if we want. Because it could not be just parametric. Usually we want to, interesting in some parametric model, inside a lot of nuisance parameter which has non-parametric. So we need to blend things. So this is what we try. And this easy, I think this expansion is very easy also because this is just a uniform expansion. But if we lose the usual LDDMM, what we have dilation in the center and we have compression in the boundary. But that's easy to think about some model to do this, and we can create something which is completely okay. And it's not so perfect, but we can make it very good if we just choose this kind of thing. Okay, so I'm concluding. So I want to say that I think that's a way to some kind of shape-aware, I call it shape-aware, we call it shape-aware metric, which is about to have a metric which depends on the shape and where you can put some information. So there is still a lot of question about how to put information, useful information, this kind of thing, how to put information in the metric. So we think that there is a way to provide easier interpretation and extraction of meaningful latent variable, because at the end what we want to look at the control variable. This is the interesting things. Okay, we say that we show that the implicit modules provides interesting new behavior. That's a natural way to introduce. There is a natural way to introduce some a priori knowledge. Well, okay, so this is clearly still work in progress. I think it's a full program where, okay, we have a very, I think we have a quite clean interpretation of the implementation of this framework, but we need still to put some GPU implementation and incorporation into KEOPS that Jean presented. Visualization tool, because the idea is to be able to help people to do something with this kind of thing. So we need to have this kind of visualization tools. It's not there at all. the analysis and to work on 3D and real data. So 3D is not a problem because we know how to do it, and the framework can be in any dimension. Okay, but this has to look at if the code is really can handle this kind of thing. But I think it will be okay. Okay, thank you.
Okay, so we have time for a few questions before the end. Question. Okay, so okay, first here.
At the end of the list, did you talk about the estimation theory for this framework?
Do we have an estimation theory?
Yeah.
No, I think this
is it?
This has to be done. But what I want to say is that I think it's the talk was more about saying that how we know more or less we can, after we say when we have a Riemannian framework, we know how to, in some way we did that, we did that, we can rephrase a lot of things in that saying. But I think the core thing is to, this metric and just, here I say, in fact, I'm saying something about the latent variable. I'm just pointing some interesting variable, and I have a way to put them in the mold. But I think, yes, you have to develop the statistical framework for that. But I think it's okay. It's something you can do many standard from here if you want.
Well, I was pointing. I think we had this discussion before. Is sort of if you have one leaf in one, another leaf in another time. There are many ways of you have these different modules of deformation, and so is there a uniqueness and identifiability? You can reach this in many different combinations of
you could
deformation.
Because it's we've seen in your talk that there is in sub-riemannian geometry we can have a lot of things happening. Yes, we can have this kind of thing. But I say in high dimension, since we are doing minimization, so at the end we have to go from one shape to the other. I think it's that's true, but I think it's
because that's one thing that Ulf
so,
never
but for
liked.
the identifiability, I think this is something to be precisely treated. I think it's
that's one thing Ulf never liked about our paper was that too many simplifying assumptions made it. He said it's no longer.
No, but I think that's the cool thing is that we have something which is the key argument is that we should have a way to update the metric when the shape is evolving in a nice way. And so I think this is more or less solved. And we can compute that.
Because I think there is a question from Hugo.
So in the shape analysis, you nicely reduce it to.
I cannot hear you.
Sorry. So in the shape analysis, you nicely reduced it to low-dimensional control problems, and then you studied the Hamiltonian flows. In these Hamiltonian flows, you use kernels. And if I understood it correct, are these Hamiltonian flows?
No, I use currents. For the data attachment term.
So I mean kernels.
Kernels.
Yeah, that's what. Yeah. Sorry. Yeah, and I was wondering because you.
No, but here, it's no more. You have you have somewhere kernel, but you have a lot of stuff in the middle.
In the middle, okay.
Because but ask your question.
I was just wondering if because you said, hey, it's very useful to include this sub-riemannian geometry in the basically in the flows and in these geometric control problems. Would it also make sense to include then degenerate diffusion kernels for the kernels of the Hamiltonian flows for the shape analysis?
Wow, surely. I think we have to discuss about that. I'm not sure to really understand.
Yeah.
So, you mean? At the very beginning, the kernel should be something which are generated in a sense.
Yeah, that you use,
maybe,
for example.
Maybe. The thing is that what we are trying, we put the constraints, so we start with something. I say, in fact, because there are a lot of discussion about the choice of the kernel and so on. I say now, that's important for the non-parametric point of view, but when you put this constraint, I think in some sense, but this is an interesting theoretical question, and we have no answer about that, really. But I think the kernel is not so much important.
So
I think
important.
in that situation, and the non-degeneracy, we get it by this constraint in a sense. So we can start with something which is pretty isotropic, but we biased it in a way. So that's the idea.
Yeah. Okay, thanks.
Okay.
Okay, so I think it's time to thank Alain for his talk and all the speakers of the conference.